my name is Dana Golden. Today we're going to finish up our unit on environmental data analysis with basic time series forecasting. What is time series forecasting? You're predicting future values based on past observations of a variable. You're assuming temporal dependence between data points. Some key concepts in time series. First off, you have stationarity. Basically, you want the statistical properties of the series to not change over time. You want it to be very stationary, and you want limited autocorrelation. So, or you want to, if you have autocorrelation in moderate, which is that there's correlation between observations at different time lags, and then lag order is the number of past observations used to predict future values. So, common time series models, you have autoregressive, which is a series depends on its past values. Then you have moving average, which is the series depends upon forecast errors. You have ARIMA, which combines AR and MA with differencing to handle unstationarity. It's very useful if you're working anywhere in finance to really remember these three models, because it's very useful to be able to say, I know how to do some forecasting. I know what stationarity is, that things aren't changing. I know what autocorrelation is, things are correlated across time. And I know what a lag order is. So here's an AR visualized. AR0, everything is really noisy because nothing depends on itself. AR1, notice that it seems kind of like observations are really correlated to past observations. And then AR2, like things seem to like move in trends. And then AR3, you kind of have these longer trends. Yeah, so go ahead, add more terms. The more terms you add, the more complex it gets. And then what these diagrams are called, it's called a correlelogram, and that helps you figure out what order of lag you need to add. And I won't get too far into that, but just if you're interested, look more into it. And so in the second of this class, we're going to look a lot at commodity markets. So that's why we're doing this look at forecasting and on time series at a basic level. You're not going to need to know this at any level of mathematical detail. I won't test you on that, but an error model is price of the future at time t is equal to alpha plus beta price of the future at t minus 1 plus epsilon. So alpha is the intercept term. In this case, because this is a time series, alpha is y bar. It's the mean value of price. Beta is the regressive coefficient relating pt minus 1 to pt. And then epsilon is a white noise error term. With how we're specifying this, we're saying after you account for these two things, the error is just a normal process with mean 0 and some variance. So the steps of doing this: obtain the historical natural gas futures price from EIA. If you're interested in doing this as a final project, we can talk about how to make this a real thing. Test for stationarity using the augmented Dickey-Fuller test. You don't need to know anything about that. Just run one and look if the p-value is good to make sure there's not non-stationarity. Fit an AR1 model of the data. Use the model to forecast futures price. So this is used for energy market price prediction, obviously, and risk management portfolio optimization. So the libraries, Tidyverse, and today we're going to be using Forecast. We have a simulated set of natural gas futures. Here we're just simulating our data using a random normal that's going to bounce around a little bit. And then we're going to convert to a time series object, so gas prices and time series of our variable with a start and a frequency. That's important. You think about when does the data start, and then how frequent are the data. Here it is monthly. And then we test for stationarity. We run the augmented Dickey-Fuller test for stationarity. We're going to say we pass the stationarity test. It's not trend. There's no trend in the data. This is probably not accurate for natural gas over the long term. Right now, natural gas is a little bit over $3. It historically has gone up like most things in the economy. But if you adjust for a bunch of things, there's still a trend up, even if you're adjusting for inflation. But if you adjust for a bunch of things, it's pretty stable in the short term. And then if you want to fit an AR1 model, you do AR model. And then ARIMA, if you're very interested in this kind of work, look up all the things you can do with ARIMA. It's very interesting. Gas prices, that's your time series. And then order, C, that's how you create a vector in R. And you can do, this is AR, so this is the number of AR terms, that's 1. This is the MA term, this is the I terms, that's 0, no integrated terms, and this is the MA terms, that's also 0, because we're just doing AR right now. And you do a summary, and that gives you the details of the AR1 estimation. So stationary, we check for it using the Augmented-Dickey-Fuller test. AR1 model, we fit using the ARIMA function. Forecast, we predict the prices for the next 12 months. And then if we want to now use our code to also forecast prices out. So if we were doing this with a linear model like we did before, we would use predict. But here we're going to forecast values goes to forecast error model, h equals 12, and then print forecast values. And then you're going to plot the forecast value alongside the label, natural gas forecast, time, and price. And so now we just forecasted the predicted price for the next 12 months. So how do you forecast with exponential smoothing? This is another type of forecast. It's a different method, and this one applies exponentially decreasing weights to past observations. Basically, the idea here is that you want to weight your forecast, but you also want to weight your prior, what you saw last. So it's a self-correcting time series forecast is actually very good. For time series with trends and seasonality, particularly trends that change pretty quickly. So you have simple exponential smoothing, which is for a series with no trend or seasonality, and this formula is just the predicted value of the next period is equal to alpha times the current period's value, plus 1 minus alpha, the predicted value in the current period. So over time, the nice thing about this is your current observations the new observation will work more and more into the forecast, and very quickly you'll adjust to new values with how quickly you do that based on alpha. So linear trend method is the same thing, but for a series with a trend, and Holt Winters is for trend and seasonality exponential smoothing. So the key parameters, alpha, which is the smoothing parameter for level, how much do you want to respond, how quickly do you want to respond to changes in the series, beta, smoothing parameter for trend, what do you think is going on with the series, do you think it's going up, and then gamma, which is the smoothing parameter for seasonality. And here's a little graph of exponential smoothing with different levels of alpha. So here's demand, here's we're trying to forecast it, and you'll notice if alpha equals 0.1, it very slowly adapts to new values in the series, and then if alpha equals 0.8, it very quickly, maybe too quickly. So you really want something, in this case, demand's moving around, so maybe we do want something that moves around this quickly, but usually you'll want something that moves around a little bit slower than this. So our code for exponential smoothing, you import forecast, you simulate some time series. Here we're setting a seed so that we're able to reuse this code and get the same values every time. Not something we always want to do, but something we want to do in this case. And then data goes to time series, simulate some data with a mean 100, standard deviation 10. We do simple exponential smoothing, data, and then 12 months, summary of SES model. And then we use the Holt linear trend smoother. We estimate that with a window of 12, able to see the past 12 observations, and then we get a summary. And we do the same with Holt Winters. So now we have the data, we have h equals 12, we have seasonality. So h equals 12 allows it to see 12 different months for potential seasonality. Then we plot the forecasts on themselves, and then you can see how all the forecasts compare. That essentially is similar to this graph, except we're not going to show you that today. And then SES is the standard exponential smoothing algorithm. Holt accounts for trends in the data. Holt Winters accounts for trends in seasonality. And Autoplot visualizes forecasts with historical data. So these are good tools you can use in your work if you ever work in finance, if you ever work in an area that uses a lot of time series forecasting. And on your homework, I've asked you to do one forecast. I'd like you to think about these methods as a way to do the forecast in R. And without further ado, I hope you have a great day, and I'll see you next time.